Yes, so Srikal students, today we're going to talk about the relationship between apparent depth and real depth. Whenever we look down uh, in some container, let's say there's an object at the bottom of the container, we feel that the depth is less as compared to the actual depth. We feel that the object is little above the actual bottom. We feel like that, and if we actually measure the depth, it will be more. So this lecture is dedicated to Willebrord Snell. This guy is from Netherlands. He was from Netherlands, but still he's there in our heart. All the scientists, they never die. And that's beauty about scientists and it's apathy of normal human being. He was a Dutch mathematician, and he again was a person who said no to homework and normal, uh, you know, routine work what students do. He went in depth and he took reflection and refraction and geometry as his research subjects. And possibly, I think this was a person, Willibord Snell, a mathematician, a physicist, and a scientist, and a great human being, who was the first one to establish large scale experiments to measure approximately, with some little bit of error, the diameter and circumference of Earth. So his students were also really crazy. So I will give the link of his biography for students to read it. So this lecture is dedicated to Willibald Snell, and in refraction, we know him very well as Snell's law, right? There are three ships in Netherlands, Dutch, which are named after him, and a lot of other uh, things in the world named after Snell. And we know Snell's law. All right, guys. So let's start with our topic uh, for today. Well, this is our container. O is the object, and at A and B are two rays emanated from O. OAL ray is sort of normal to the surface. XY is the free surface of this liquid, which we are considering as medium with, optically high density, optically denser medium, and above this is air. So xy is a boundary of this. Xy as plane is separating the optically denser medium from optically rarer medium, that is air, which we have named as A, and optically denser medium we have named as B. All right, students. So this ray is normal, and we know that we did discuss that day that if a ray is coming into from rarer medium to light, from denser medium, exactly perpendicular, so book says it's not, there's no refraction. There is refraction. There is refraction. So one ray OAL perpendicular, and other ray from O, this is the object at the bottom of the container, this container, outlined with red color. And the second ray is, as is going away, let's say OB. You could have taken B here also, here also, here also, you know, that doesn't matter. But I've taken here B for the convenience of drawing. So obviously, you know, we have angle of incidence and angle of refraction. So we can say that NBC is angle of refraction. This ray is going out, and we can say that OBN dash is angle of incidence. Okay, guys. So uh, you see that ray of light OA incident along normal to the surface of the liquid will be refracted as such along AL, and another ray of light OB on refraction into air bends away from the normal NBN dash. NBN dash is a normal, so it bends away from the normal, which is the case whenever the ray gets refracted into a rarer medium from denser medium. So it travels along BC. The two refracted rays appear to come from I. This is important. For us, because of this refraction, I sees that they're coming from our eye. Our eye gets illusion that these two rays are not coming from O, rather they're coming from I. Where is I? That's extension of BC. 1 second, students. We use red color. So this is extension of BC. That is BI. Well, I've drawn quite high. Should be a little down. We'll draw a little down. 1 second. Yes, this is I. Okay. So it looks that both the rays are coming from I, not from O. And that is the reason behind our wrong assumption about the location of point O. We think that it's at I, not at O. Okay. So uh, for us, the real, the apparent depth, we feel so. Apparent depth is like the apparent velocity. Relative velocity is apparent depth is AI. But actually, whereas Ishma Anand, what is the real depth?
AO.
Beautiful. The real depth is AO. That's just great. Okay, because actually the object is at O, not at I. But we feel that they're coming from I, what the rays. Okay. So guys, you see that let's say this angle OB and dash is equal to I, OB and dash as we have written, and angle NBC is equal to R, angle of refraction. Okay. So now guys, what is the refractive index of medium A with respect to medium B? Medium B is water. Medium A is air. Can anyone say refractive index of medium refractive index of medium A with respect to medium B? Anyone? So medium A has which angle? R. So Ishma, it will come in the numerator or denominator?
Denominator.
Denominator. Beautiful. So it will be sine R, sine I by sine R. This is a way to write this. Okay. You can also write this like this. Some books might end up writing this uh, A B. Refractive index of medium A with respect to B. It doesn't really matter. You can always write like this also. Refractive index of medium A with respect to B. So it's just that how you write doesn't matter. Whatever is your name, it doesn't matter. You have different names. The person is same. Okay, so this is I, and we also know that students mu AB is equal to 1 by mu BA. Am I right? So from this we can easily say that mu BA, that is refractive index of B, denser medium with respect to A, would be equal to, yes, it would be,
Sin R by sin A.
oh, that's just beautiful. Sine R by sine I. Let me change the color. Different color. It's very costly color, but I can use it for you. Okay. So students, you see that uh, angle AOB is equal to angle OB and dash, right? AOB. This angle is equal to OB and dash is equal to I. You agree? Right? So we have this right angle triangle, which one? AOB. So in this right angle triangle, students, quickly we can do uh, OAB. AOB. Fine. AOB or OAB or BOA, doesn't matter. Okay. So, yeah, but then some people say this is not the right way to write this triangle because this right angle should come in the center. Okay, so fine, let's agree with the mistake and let's write OAB. So what is sine I? Tell me quickly. What is sine I? This is I. This is I. Angle O is I. What is sine?
AB by OB.
Oh, beautiful. AB by OB. Oh, that's just great. AB by OB. Now you see that angle AIB is equal to angle NBC. Do you agree? Angle AIB. AIB. This angle. Right? This angle is equal to NBC is equal to angle R. So in this triangle, which triangle? Now we take triangle IAB. IAB. Triangle IAB. In triangle IAB, what is sine R? Gurjot? This is R, this is also R. Triangle IAB.
AB by BI.
Oh, that's beautiful. That's great. AB by BI. Beautiful. That's great. So quickly, now we are rushing towards our end. Let me make it a little lighter. So substituting all these values sin I and sin R in this mu BA. What is mu BA? Refractive index of material B with respect to A is equal to, yes, tell me fast, sin R by sin I. Sin R is AB by BI divided by, come on guys, help me, AB by OB. So Ishma, that is equal to, AB will cancel with A.
OB by IB.
Oh, that's just great. OB by IB. Beautiful. Let me change the color for you. Okay. OB by IB. That's good. You see, students, this is our I. Now, both these rays, AL, OAL, and BC are being observed by our eye. Beautiful eye, beautiful lens God has given us. We never complain to Him. He's given a lot of things. So both these rays are being observed by our eye, which is getting, confused whether it is at I or is it as O. So I thinks this I means our Ankh. It thinks that the object is at I. Okay, maybe the brain is sometimes telling no, it's wrong. But what is it? There is that tussle happening between eye and brain. Okay, so eye sends a signal to brain that it's at here. Okay, the object is here. So but both these rays are being watched by the eye. Maybe the brain is telling, no, this is a denser medium. You may be wrong, but then, okay, fine, it's happening. So, but the rays are, the aperture of eye is small. So, for that, you see, students, for BC and AL both to reach I, do you agree with me? B should be as close as possible to A. You getting it? Are you getting it? B should be close.
Yes, sir.
His father, BC might, BC might reach away from the purview of I, and AL might reach here, right? So I may not be able to judge the depth, right? So that's it. It's important. So I think you got it. B should be close to A. If B is close to A, students, so then I can always say, one second. I can always say that OB is approximately equal to, can anyone tell? OB is approximately equal to, come on, B is close to A, limits and derivative. So OB is approximately equal to OA, and also IB. Come on, students, you should speak. We know things, and we're not able to transfer to younger generation, our thinking can be questioned by people. IB is equal to, approximately equal to, anyone?
OB,
No. IB. See, B is close to A. So when B is far from A,
IA,
yeah, IB is greater than IA. It's approximately equal to IA. Beautiful. So I can always say now what? Mu BA is equal to, come on, tell me the next step fast. It's OB by IB. I can write OA by IB approximately equal to IA. Is it right? Now what is OA? Anyone can tell me? OA is this, uh, is this
real depth,
beautiful? That's right. This is real depth. Or you can say T, the thickness of refracting surface, this medium, thickness of refracting medium, real depth, divided by what is IA, Gurjot, Daksh.
Apparent.
Yeah, beautiful. Are you enjoying the video?
Yes, sir.
Apparent depth. All right. Oh, we don't have any name for apparent depth. Okay, that's good. So this is our equation. Okay, this is also second equation, and let me name this as first equation, sine r by sine I, first equation. Okay, guys, this is beautiful. So now, actually, object is here, but we think it's at I. So students, this distance, IO, you know, uh, object appears to be raised from its position O to its apparent position I, right? The distance OI. This distance through which the position of object appears to be raised is known as normal shift. Yes, students, it's known as normal
Shift.
shift, and it is denoted by D. Okay, so I can say D is equal to Ishma OA minus, very good girl, D is equal to OA minus, come on, anyone? Array, this is normal.
IA.
Correct. IARAI. Beautiful. Beautiful. Okay, fine. So this is equal to, can I write OA? Can I take OA common? So I will write 1 minus AI by OA. Maths is always there. This is equal to OA into 1 minus 1 by, come on, Dakshnur, 1 by OA by AI. That's beautiful. Yeah, students, what is OA? OA is the thickness of refracting medium or the actual depth. Let me make it T. T for thickness. 1 minus. Anyone can tell what is this? Already we have understood what is this? OA by AI.
Real
mu
depth about
BA,
What is that? Can you explain? Refracting index of,
mu BA,
the refractive index of medium, denser medium with respect to rarer medium.
rarer medium,
All right, students, with the grace of God and with your support, we have been successfully able to derive the expression for what is this? D is known as normal shift. See, students, it's interesting to know as D is more, D will also be more. What does that mean? The object will appear to be raised more if the thickness of the refracting surface of, or you say that if its actual depth is more, so it will look like more elevated. Fine. Number two, the D, the normal shift. Normal, why its name is normal shift? Because it's shifting towards normal. There's a shift. We this object appears to be shifted from the actual position O to a apparent position I. That's why it's known as normal shift. It also depends upon the what? Tell me. It also depends upon, see, if this is more, if this is more, this will be less. If this will be less, 1 minus this will be more, and hence d will also be more. That is absolute refracting index of what? Medium B. That is more denser is the medium, the more normal shift we will observe. मतलब हमें लगेगा कि ये ज़्यादा ऊंचा है अगर इसकी थिकनेस ज़्यादा है और अगर इसका रिफ्रैक्टिव इंडेक्स ज़्यादा है, चाहे आप ये बोल दो कि इसका एब्सोल्यूट रिफ्रैक्टिव इंडेक्स ज़्यादा है, चाहे आप ये बोल दो कि इट्स refractive index with respect to A is more, normal shift will be more. Okay, so this is, uh, the derivation. Hope you liked it. Share with your friends. So we can do a little numerical also. See, velocity of light in glass is 2 into 10 raised to power 8 meter per second. And in air, it is 3 into 10 raised to power 8 meter per second in air. This is in glass. By how much would the ink dot appear to be raised? Is the ink dot? By how much distance it will appear to be raised? That means they are asking about normal. Yes, Gurjot. They are asking about normal
Normal shift.
shift, which we have named as D. All
D.
right. And we know D is equal to, would you be kind enough to tell? T into
Into 1 minus
minus
1
1
upon.
by refractive index of denser medium with respect to rarer medium. Beautiful. So which covered by glass plate 6 centimeter thick, right? This glass plate is 6 centimeter thick. It's covered by a glass plate, it's like the dot is here and this is a glass plate over the dot. So by how much it will appear to be raised? Such a beautiful question. So students, first I can find out the mu. What will be mu? See, mu can also be find as in terms of ratio of sine. It can also be find out in terms of the velocity, the ratio of the velocity. So it will be 3 into 10 raised to power 8 divided by 2 into 10 raised to power 8. So it will be 1.5. Got it? This is refractive index of glass. This is also the way we find out. Okay, 1.5. So we know it's 1.5. And now what will be D, students? Very simple. D would be, yes, Ishma, in centimeter. D thickness is 6 centimeter into, come on, 1 minus 1 by 1.5. So it will be equal to 6 into 0.5, because 1.5 minus 1 is 0.5 divided by 1.5. So it's 3. And how much will be the lateral shift? Come on, students. Normal shift, I'm sorry. How much would be normal shift? I think I got to
So we'll take 6 in meter.
Pardon me? No problem. Don't worry.
We will
Don't worry. The answer will be in centimeters. So
2
it's
centimeter.
beautiful, 2 centimeter. All right, students. Hope you liked it. Uh, Stay blessed and stay happy. Say no to everything, but not concepts. This lecture dedicated to Snell, and I really wish that one of you listening to this video go deep into the concepts and enjoy physics. Have a nice time.